Alright, so briefly I'll be speaking on the Newton method, and it's a faster way to find our root within the given boundary. So, as the Newton method states here, it says zero finding the special case. It says the linear approximation based on one point x1 y1 only is given on one point x1 y1 only, given by y equals y1 plus x minus x1 into f prime of x, and we've now had a condition to work with this. As soon as there's an example, we'll be looking at that. But currently, the example we have here, we are working with this formula that says y into n plus 1 equals yn plus 1 equals yn plus yn plus 1 yn plus 1 equals yn plus x n plus 1 minus xn into f prime of xn. But what everything basically simply implies is the formula that boils down to this x n plus 1 x n plus 1 x n plus 1 equals that would be xn minus f of xn over f prime of xn. So now basically f prime of xn is saying find the y dx of xn. So moving down here, the advantages of the Newton method. So starting point x1 can be arbitrary, so the convergence is faster than the previous two methods. When it says starting point x1 can be arbitrary, it says it's basically saying for n equals 0, you can choose an arbitrary value. So basically you can choose an arbitrary value for x naught. If you look at the example here, an arbitrary value was chosen. So basically, let me run that back to the advantages. Starting point x1 can be arbitrary. The convergence is clearly faster than the previous two methods. One disadvantage is that you need to do differentiation, which is the y dx, as I stated here earlier, and also said the divergence may occur. So let's see how all these things factor into the example given here. So I'll move right down to this example. So this example here says we are still working with this function f of x equals x squared minus 1, right? And then if you're looking at this, trying to solve the root of this x squared minus 1 equals 0, x squared will be equal to 1, x is square root of 1, and x will be equal to 1. This is the value we are looking to approximate towards. This is the value we are looking to approach. Working with this, looking at the Newton's method, the formula here says x n plus 1 equals x n minus x f of xn. So now what is our f of xn here? So f of xn here says that means there's a g of n that is bigger than f of n. Remembering f of xn over, let me just write again, f prime of xn. So looking at this function, our f of x is x squared minus 1. So working with this, we are going to have xn. So we're going to substitute, we're going to do this f of xn. We are going to substitute xn everywhere we find x. So we're going to have f of xn equals what? X of n squared minus 1. Right? So, and then the second one says f prime of xn, that is differentiate this. So differentiating f prime of xn, so f of xn, right here, equals xn squared minus 1. So f prime of xn equals to y dx, right, of f of xn, right? So differentiating this, the way differentiation works basically, if you are differentiating x squared, you have 2x. If you are differentiating 2, you have 0. If you are differentiating x cubed, you have 3x squared basically. So our example, our function here says xn squared minus 1. So what this will result into will 2x n, now basically minus 0, which is basically 2xn. Alright, so working with this formula, we have xn minus our f of xn, which is xn squared minus 1, and like we solved in the last slide there, and we add them to differentiate xn squared minus 1, which are mounted into 2x minus 0, and 2x minus 0 is 2x, so we have 2xn, right? Now I'm going to do this, I'm going to find the LCM here, which is 2xn. So 1 is this, give it 2x of n, multiplied by this, you're going to have 2xn right, minus this will give you 1 minus x square minus 1. So yeah, so we're going to have 2x square n minus x square n plus 1. We're going to have this over 2xn. Based on the order of the function, like here, the order of the function was from here. So our C will probably be the next value after this, that's after 2. So C will be 3. And identify the base n naught. Here it was 0 because this is negligible. This did not really happen. There you go. Okay? Come on. Yeah, so moving on. This is a recap of big omega. This is an example. This is a recap of big theta. We discussed that in the previous lecture. Okay. So now this is the next thing I want to solve that again. This is the key slide in this lecture. You need to understand which the magnitudes of orders. From this slide, it said log n is smaller than n. N is smaller than n log n. So we have 2xn squared minus n squared is smaller than n cubed and n4 and squared plus 1. N raised to power 4 is smaller than 3 raised to power n or smaller than 3 raised to power n. What we have here is now some 2xn squared minus xn squared. So that will be x of n squared, right? Plus 1 over 2xn. So basically the coefficient of this is 2, coefficient of this is 1. Subtract, you have 1. So you have 1x of n squared. So basically that is still xn squared plus this one. The way we got this one is 2xn will give you 1. 1 multiplied by this will give you exactly this. And then you multiply through by minus. That's how we got plus. So working with this, we have xn squared plus 1 over 2xn. Okay, so bringing this out, we have 1 over 2 into xn squared 1 over 2, right? We have xn squared plus 1 xn squared first example is f of n squared is equal to plus 1 log n squared over xn. Remembering our former rule, log x over xn. So just to make this simpler, basically I have 1 over 2 1 over 2xn into xn squared plus 1. So this eventually becomes our formula for our Newton's method after evaluating this formula, which is xn minus f of xn over f prime of xn. So for every single formula that you are given, and then for every single function, say your function is x cubed minus 1, this is probably not the formula you get. It's probably not the answer you get, because you are going to use the exact function as given to you. So we eventually used x squared minus 1 because x squared minus 1 was given to us. We differentiated x squared minus 1 because that was what was given to us. If we're given something different, we wouldn't have used this. We would have gotten a different formula entirely. So this formula you get is what you use to perform your iteration. So as the iterations move towards your value, which is 1, you keep running your iterations until you get the value that is as close to your aim, which is 1, as it is here. So let's perform our iterations. So using our formula 1 over 2xn to xn squared plus 1. Now we need a value, says xn plus 1. Now where n equals 0, right? So we have x naught plus 1, which is x1. So x1 will be equal to 1 over 2 x naught. Since you don't have x naught, you have to assume a value for x naught. So I'll advise you that you always choose a value for x naught that is as close to the lower bound as possible. Our lower bound here is 0, and the lower bound is 0, and the upper bound is 1.5. Upper bound is 1.5, so it's always better to choose a value that is closer to the lower bound as much as possible. That's why we have 0.1 here. So 0.1 is our x naught. So we have x1 equals 1 over 2xn, which is 2 into x naught, 2 into 0.1, then multiplied by xn squared plus 1. Our x naught is 0.1, so 0.1 squared plus 1. So if you evaluate this, can I just work with 0.1 squared minus 1 plus 1 rather. 0.1 squared will give you 1.01. So we have 1 over 2 times 0.1 into 1.0. I advise you just remember the arithmetic series, geometric series, and this special case. So these three are very important. 1.01. Now finally, so multiply this, you have 1.01. You have 1.01. Any mathematical statement is true. For instance, if I say a function s of n is true divided by 2 times 0.1, 2 times 0.1 gives 0.2. And have to prove for subsequent values of n greater. So working with that, 1.01 divided by 0.2. 2n plus 1 is less than or equal to 2 raised to the power n. That gives us 5.05. So now we have our value for x1. Now for the next one we're looking for is going to be where n is equals to 1, to be xn plus 1. When n equals to 1, we have x into 1 plus 1, which is x2. So our x2 now will require a value for x1, which is 5.05. And we already have a value, so x will be 1 over 2 into 5.05 into 5.05 squared plus 1. So to evaluate that, you're going to get 2.624. So you keep iterating until you get something that is as close as 1 as possible. So if you see you're on 2.624, that is still very far from 1. Then you continue, you can see here they go 1.5026. You iterate again, you get 1.084, and you iterate again, you get 1.003. So basically the way it works is get this, understand this formula, get this formula down. Once you get this formula down, for any single function you are used, substitute xn as x in the function. If it is x squared minus 3, substitute this xn into x. So it does not, this formula you're seeing here, this 1 over 2xn into xn squared plus 1 does not hold for every single question. It depends on the function that is given. So x squared minus 1 is given this. X squared minus 3 will give you something different. So what you need to do is put f of x, put xn into x, and then the second one, put xn into x, but then differentiate it. Then the value you get will eventually give you the formula you use for your iterations. So basically that is how the Newton method works. Thank you very much.